So it's just okay. So today we're just going to be going over a bunch of problems, right? That, reviewing the content that we've learned over the past 5 lessons, and maybe going through some new content if some of these problems does require it. Because normally, I don't normally teach a geometry class. I'm not sure what you guys have learned, right? Um, okay, cool. So, oh, I should probably be sharing my screen, huh? Yeah, cool. Okay, so there's gonna be three levels of difficulty, right? We've got the hard problems, the harder problems, and the hardest problems. Okay, I'm not sure how many of these we'll get through. I'm gonna try get through at least the hard and the harder problems, and we probably won't have time for all of them, but yeah, there are 9 problems in total. Okay, so the way this is gonna work is I'm gonna present the problem. Um, you guys might want to put up the problem on your own screens because I will be also at the same time drawing up the diagram on GeoGebra on the side. So I'm not gonna have the problem like on my screen at all times, right? So you might want to just pull up yourself so you can have it for reference. I would recommend trying to draw the diagram yourself, but I will also be drawing it like on my screen, right? Um, yeah. Okay, so we have the first problem here from Beamer 1. Okay, so we have a triangle ABC, and we have a foot of a perpendicular from B to CA, right? Okay, so oh god, let me just sorry. Oh, okay, you know what? Sorry. You guys like while I'm drawing the diagram, you guys should probably try just work on the problem yourself, right? So this is the time that I'll be giving you guys to work on the problem yourself. Also, I'm sorry, I'm gonna have my camera off. Dawn's not here to, chase me up about it. Just because first of all, I feel like, what I'm sharing on my screen is more important than my camera, and also I might be eating something in the middle of this, and I'm not trying to turn this into like a mukbang session, right? Okay. Okay, before we start with this, I just want to ask, is everyone here like comfortable or familiar with like properties of cyclic quadrilaterals? Is this something you guys have covered in a previous lesson? Okay. No one's replied. Is that yes or no? Okay, I'll just assume it's a no. So I'll quickly go over like basic properties of cyclic quadrilaterals. I mean, cyclic quadrilaterals are probably one of, if not the most important, like concepts in geometry, right? Olympiad geometry at least. And a lot of the times, a key step in solving a problem is realizing that 4 points lie on a circle. You found a cyclic quadrilateral, right? And oftentimes they're kind of hidden and maybe tricky to find. But when you find them, you get a lot of useful information, and it helps you get like new information that you didn't have before finding it. Okay, so what is a cyclic quadrilateral? It's defined as a quadrilateral or whose four vertices lie on a circle, right? Um, you know, where if I just have some random circle like this, a cyclic quadrilateral here would be something like H, J, K, L. That's a cyclic quadrilateral. Okay, so what properties do cyclic quadrilaterals have? Um, the first property is that the opposite angles in the cyclic quadrilateral add to 180 degrees. So if I look at this angle, LHJ, and I look at the angle JKL, you see that 92.23 plus 137, that should be 137, right? Um, these add to 180 degrees. Um, and this is an if and only if property as well, right? So if I find a quadrilateral which has two opposite sides, well, sorry, two opposite angles which add to 180 degrees, then I know it's also a cyclic quadrilateral, right? So a cyclic quadrilateral means opposite angles add to 180. Opposite angles add to 180 means this is a cyclic quadrilateral. Okay, cool. That's the first property. The second useful property is that because angles subtended by the same arc of a circle have equal size, we can say that these two angles, these two angles are equal. LHK and LJK. Here they're both equal to 61.4 degrees, right? And that's just because they're both equal to like the angle subtended by this arc, LK of the circle, right? So and it's not just these two angles are equal, right? Like if you look at this pair and this pair, maybe I'll just make them different colors just to highlight this a bit better. These two angles are also equal. And similarly, you have two more pairs, right? So you get quite a lot of pairs of equal angles once you find a cyclic quadrilateral. And that's why they're so useful. Um, if I show that the green angles are equal, then I've also shown that the red angles are equal, right? So if you can show that like these two corresponding angles in any quadrilateral is equal, then you have also shown it's a cyclic quadrilateral from which you can get a bunch more properties. So that's why cyclic quadrilaterals are very cool, right? And you should always be on the lookout for them. Conjecturing, right? If 4 points look like they could lie on a circle, maybe try to prove it, right? See why or why not. Like why they are cyclic or why they aren't. Okay, I'll just delete this now because it is a bit distracting. Okay, so getting back to the problem, the way it's defined is we have a triangle ABC, and we have this angle, though this point E, such that BEC is 9 degrees. So it's defined to be 9 degrees. We have this line BF such that BF is tangent to the circle ABC. And then you have a point F such that CFB is 9 degrees as well. Okay, so there's gonna be two main like okay, first of all, I guess obligatory question. Does anyone have any ideas, or has anyone like noticed anything about the problem that could try help help you solve it? Sorry, the statement is to prove that AB and EF are parallel. So these two lines here, this one and this one. Okay. Um, okay, that's fine. Does everyone here remember the alternate segment theorem? I think this was covered in a previous lesson. I went through some of the old material. No, okay, that's fine. So the alternate segment theorem is very it's a very like common and important theorem. So this one's definitely worth learning, and I would say it's the most like useful thing to try whenever you see a line tangent to a circle, like you see in this problem. Okay, okay, I'll get back my oh wait, never mind. I'll get back my circle here, right? That's fine. My circle D sub T, and I'll have a tangent to it. So okay, I'll just okay, maybe I'll do it like this, right? Okay, let's say I have a line that's tangent to a circle through a point G. What the alternate segment theorem tells me is that if I have a like kind of like a triangle um coming out of it, then I have that this angle. Oh, sorry, not that angle. Um, this angle equals this angle, right? Here they're both 53 degrees. This angle equals this angle. And again, I guess I'll just quickly make these different color. Right. So it's kind of the angle that's like up against that's adjacent to this side of the triangle is equal to the um angle opposite the side of the triangle, right? This one equals this one equals this one. And this is a very important thing to well to learn to memorize, right? Because whenever you see a tangent, that actually gives you an equal angle condition. And equal angle condition is much better than a tangent, right? Because what the hell do you do with like what the hell do you do with a tangent, right? It doesn't really give you too much, but equal angles gives you a lot. It gives you, cyclic quadrilaterals, similar triangles, like parallel lines, stuff like that, right? Okay, so let's take this like theorem and try to apply it to this problem, yeah? Wait, what angles do you guys think are equal using this theorem? Remember that this line BF is tangent to the circle at B. Yeah, maybe it would be a bit more helpful if I get rid of some of these distracting ones, right? Do you see the similarities between this configuration and this configuration? Don't worry if you don't see it. Okay, look, I'll make it a bit more obvious. Wait, I got it. Do-do-do-do, do-do-do-do. Wait. Okay, so given that the green angles in this diagram up here are equal, right? The green angles are equal and the red angles are equal, right? In this diagram up here. What angles are equal in this diagram down here, which is our actual problem? Man, I'm sure I'm not like eat a burger while I wait. Yeah, yeah, nice. Okay. Okay. Thank you, what, Jonah, for you know answering, right? Yeah. So angle A, or the angle right next to A, right? This angle is equal to this angle. The one like saddled between like BF and BC, right? So angle BAC is equal to angle FBC. Cool. So I'll just get rid of that and I'll add the rest of what if we had back. Okay. And that's pretty good. That gives us a nice like interpretation of the tangent condition, right? We've turned the tangent into an angle condition. This angle equals this angle by the alternate segment theorem. And just a tip, whenever you see a tangent to a circle, always try using the alternate segment theorem in some way. It normally turns out that it's probably unuseful. Okay, but we want to prove these two yellow lines are parallel, right? Okay, what angles? I mean, okay, so normally when we're trying to prove that lines are parallel, a good idea is to prove that like some angles are equal, right? For example, what angles do we know are equal? Like given two parallel lines. Okay, maybe I was phrased a bit badly. Anyway, it would be nice, I guess, right, if we could prove that this angle, BAE, was equal to the angle FEC, right? If we could show that this angle, was the same, right? Then we would have shown it's parallel because, well, because that's just a property of parallel lines, right? Okay, but we know that angle BAC is equal to angle FBC, these two angles highlighted in green. So we want to try show that the two green angles is also equal to this blue angle. Okay, how do we do that? Hmm. Well, I'm not sure if you guys remember, but right, if you remember from earlier, this was one of the actually one of the properties of cyclic quadrilaterals, right? You would have that the angle opposite this side, FC, the angle at B would be equal to the angle at E because it's like subtended by the same arc of the circle, right? So if we can show that the quadrilateral ECFB is cyclic, then we can show that this blue angle is equal to this green angle is equal to the other green angle. And once we've shown the blue angle is equal to the green angle, we've shown the lines are parallel, and the problem is proven. Yeah. Okay. So I mean, now it's like the next you know the final step. How do we show that quadrilateral BECF is a cyclic quadrilateral? Does anyone have any ideas? Remember the two ways of proving, it's a cyclic quadrilateral. Well, two main ways. It's showing that two opposite angles add to 180 degrees, or showing that two of these like adjacent angles are equal. Oh, okay. So cool. So angle. Wait. Okay. So Jonah says angle BFC and BEC are the same. Wait, BFC and BEC. That's true. They are the same, but that we don't want them to be the same. We want them to add to 180 degrees. Because remember um for a cyclic quadrilateral, the opposite angles, they need to add to 180 degrees. The angles that are the same is like the angles that are like opposite the same side. So for example, BEF and BCF, they're both opposite the side of BF. So those ones are the same. Yes, but the two are 9 degrees, yes. So they add to 180 degrees, right? Exactly. So BEC and CFB, they're 9 degrees. Therefore, they add to 180 degrees. Therefore, BECF is cyclic. So in fact, this blue angle actually does equal the green angle, right? Okay, I'm not sure what color these other ones are. Yeah, something about there. This one? Yeah, so good enough. Wait, that's not good enough. Oh. Okay, whatever. So these three angles are all equal to the same green angle. Therefore, FEC equals BAC. Therefore, the two yellow segments or the two yellow lines are parallel. So cool, we're done with the problem. So I think that problem is a good demonstration of why being able to locate cyclic quadrilaterals is important because we use the fact that the two opposite angles add to 180 degrees to show it's a cyclic quadrilateral. And then we use the fact it's a cyclic quadrilateral to show that these two angles opposite the sides FC are equal, which is non-trivial, right? Which is something that something that we couldn't have gotten without finding that's a cyclic quadrilateral. Okay. I'll probably move on to okay, I'll move on to the next problem now. Problem two. Okay, another BMO one. Problem two, about the same difficulty, I guess. Oh, actually, yeah, okay, probably about the same difficulty. The circles S and T touch at X. Okay. Um, yeah, so you guys look at the problem on your own and maybe draw a diagram, try for a bit, and I'll draw it myself as well. Okay, I can't think of a quick way of um oh, that should be fun. Okay. So here we have a problem, right? A problem says that we have two circles S and T which touch at um okay, mm, I'll name them. Circle S and circle T which touch, which means they're tangent at a point X. And they have a common tangent. So here we have a common tangent, which is, tangent to S at the point A and tangent to B at, sorry, to T at the point B, right? So these two are tangents. Let AP be a diameter of F. Sorry, I have S. Sorry, I have named this F here. That should be point P. So AOP is collinear, right? Because the diameter always passes through the center of the circle. And now we have to show that BX and P lie on a straight line. Okay. So this problem is a very good example of just angle chasing, right? You guys all know or remember Thales theorem. I think you guys probably did learn this at some point. I mean, at least I remember seeing it in a past, you know, lesson slide. Yeah, I'll quickly I'll go over it again. So I mean, like it's not a very deep theorem. All it says, maybe you've even encountered it in school, right? It just says that if you have um you know a diameter and then you connect it like to a point on the circumference, then the resulting angle you form is 9 degrees. Like as I drag E around, this will always be 9 degrees, right? That's what the theorem is. So okay, also I might just I know you guys are all very eager to answer, but I might just have to move on ahead without waiting for any answers because it feels like I guess yeah, whatever, you guys don't want to talk, that's fine. So I'll just spoil it. Okay, I'll just spoil what you're meant to do, right? Okay, let's connect this segment AX first. Because we have AP as a diameter, we can use Thales theorem to tell us that AXP is 90 degrees, right? We know it's 90 degrees because of Thales theorem. So we want to show that PXB is a straight line. Okay, I mean, one of the ways of showing it's a straight line is just showing that the angle formed by the 3 points is 180 degrees. Yeah, any straight line, if you take an angle on it, it's gonna be 180 degrees. Well, we've shown that AXP is 9 degrees, so it remains to show that the other side of it is also 9 degrees, right? We need to show that BXA is 9 degrees. So this angle here. It's not perfect because my diagram is a bit bad, but it's okay. We want to show that this red angle here is 90 degrees. So how to do that? Um, I would ask if anyone has any ideas, but maybe I'll just stop asking that now. Although, if you have any ideas at any point ever, please feel free to drop them, right? Even if they're wrong, even if they're stupid, I don't care, right? Like I just it'll be like, come on, just you guys can say stuff, right? It's chill. It's a very very welcoming environment here at the minors and lessons. Okay, I mean I think there's quite a few ways you can do this, right? You could introduce the center of circle T, right? You could introduce this center and connect up this, which is collinear. They pass through the point of tangency. I won't do that. I think what I'll do is I'll just I'll use a property like the property of equal tangents again. I don't know if you guys know this. I don't know. So I'll quickly just say what it is. It's when you have a point and you draw the two tangents to a circle. If I can find the tangent function. Yep, here we go. If you draw the two tangents, then the lengths, right? The lengths FG and FH, they're equal. So look at, they're both equal to 3.18, right? Maybe I'll just mark it with some whatever else, right? And they're equal. Well, you can show it by connecting by connecting G and H to the center and then using congruent triangles, or you can kind of just like argue like quote unquote like bisymmetry, right? Like it feels pretty like obvious almost that they should be equal, like in equal like equivalent in length, just because like the circle is like very symmetric, and there's no reason why one side should be longer than the other, right? So that's like the property of equal tangents. Okay, so what I'm gonna do is I'm gonna just draw in the tangent. You don't have to do this, by the way. This is like a smarter way. But you could just angle trace, right? At the end of the day, you could just use isosceles triangles, use whatever, and just mark a bunch of angles. Remember that angle, BAO is 90 degrees because a tangent, when you have a tangent and you connect a line from the tangency point to the center of the circle, then the resulting angle formed is 90 degrees. But okay, if we draw a tangent from S here, notice that that this is a tangent to both of the circles, right? Because they're both tangent at X. This line IX is tangent to both the circles. So what that tells us is that segment IA is equal in length to segment IX because of the property of equal tangents on circle S. But then also segment IX is equal in length to segment IB because of the property of equal tangents on the circle T, right? IX here and IB because they're both tangent to T from the point I. Okay, so we have our setup here now, right? Where we have our triangle AXB, and we have like these three equal lengths. And whenever you have something like this, you know automatically that it's actually a right triangle. Why? I'll just quickly prove it here, right? Whenever you have and remember this, by the way, this is something else that's also very important. It'll probably come up quite a bit. In fact, it comes up quite a bit in the later problems. So just warning, right? But if I have but yeah, sorry, if I just quickly make a triangle here, I take the midpoint of the hypotenuse and I connect it up, then I get three equal lengths here. And the reason is because, okay, so I'll just quickly mark that this is a right angle. The reason is because if you look at triangle MJK, it's an isosceles triangle. So therefore these two angles are equal. But if you look at triangle MJL, it's also an isosceles triangle. So these two angles are equal. And we know that, so green plus green is equal to green, red is equal to red, right? But we know that the angle sum of the triangle is 180 degrees. So green plus red is 180 degrees, which therefore means that green plus red is 90 degrees, right? Which is exactly this angle here in the middle, is green plus red, right? So using that like calculation with isosceles triangles, you show that this angle is 9 degrees. And similarly, if this angle is 9 degrees, it's not too hard to show that these like that these lengths MJ, ML, and MK are all equal. So this is actually also a pretty important fact. It comes up quite often, where you have a right triangle and you have a midpoint of the hypotenuse, and you have three equal lengths like this. Okay, so I'll just leave that floating there. Okay, well, yeah, so we're done now, right? Because we've shown that IA equals IX equals IB, where I is clearly the midpoint of AB, right? And using the same angle calculation we did, where this angle equals this angle equals this angle, and this, they added 180 degrees, we've shown that angle AXB is indeed 90 degrees. Therefore, this angle across X, right, is 9 degrees plus 9 degrees, 180 degrees. So we have shown that it's in fact collinear. So that's good. And yeah, okay, time to just delete everything, I guess. Well, bye-bye. Cool. And we'll move on to our final problem for this section. Okay, what else is? All right, cool. Hey, okay, we're starting with a second quadrilateral. Yeah, again, feel free to like try the problem yourself first. Okay, so here's our diagram. I just finished drawing it up. So we start with so we're given a single quadrilateral at the start, right? We're given a quadrilateral ABCD. Those are the points in blue in my diagram. And we're also given another point F, which is the arc midpoint of minor arc AB, right? So it sits on the circle right in between A and B. And then we basically connect up some points like this, right? I mean, you connect up DF and AC, you get point P. Then you connect DP and FC, and you get point Q. And okay, that's very similar to what we had before, where we're trying to prove that I'll color them these nice orange color again. We're trying to prove that these two orange segments or these lines are parallel. Okay. So how to do that, right? Hmm. Well, okay, the first thing, maybe you might see. Actually, okay, I'll give a bit of a spoiler, right? A bit of a hint. There is another hidden cyclic quadrilateral in this, right? So yeah, shut up again, right? Cyclic quadrilateral, very cool. But this time we showed the cyclic quadrilateral not by showing opposite angles at 180 degrees, but by showing like two of those like angles which are meant to be equal are in fact equal. But by two of those angles, I mean like the angles opposite the same side. So first, let's just say we're working on this problem, right? Like what might we do first? Well, we probably should use the fact that F is the arc midpoint, right? And F being the arc midpoint, nicely translates to these segments AF and BF being equal, right? So I'll just mark them as equal like this. Cool. And in fact, when you have, two equal sides of the triangle, that translates to a nice angle condition as well, right? We get that these two angles are equal, and equal angle conditions, like I said before, are always welcome, right? So these two green angles angles are equal. But now we have angles on a circle, right? Like what do you do when you have angles like this position on a circle? I mean, you can kind of like move it around, right? Like as I'm like for any point, E, um on the circle, I have that BAF equals BEF because they're both subtended by the arc BF, right? And like I can move E around anywhere, and it's gonna have the same um it's gonna have the same angle, right? That's why when you have equal angles, like on a circle with like kind of circumference here, it's very powerful because you can move it around and you can get a bunch of equal angles. In fact, we have one such example right here, right? I mean, angle BDF, or the angle at D, is the same, is subtended by the same arc as this green angle here. Similarly, this angle is the same as this angle over there, right? So we have that these two angles, BDF and FCA, they're also equal to the green angle by properties, by circle properties, right? Great. So now we have four angles that are equal. Hmm. Okay. Does anyone happen to see maybe where the cyclic quadrilateral is hiding now? Hmm. Okay. Well, it's I mean, okay. Focus. Well, I'll give you a hint. Focus on these two green angles here. This one and this one. QC. Sorry, QCP and QDP. Okay. Well, time's up. The hidden cyclic quadrilateral is the quadrilateral PQCD. And it's cyclic because you have that these angles, right, which are opposite the side of PQ are equal. Um, right, like this green angle equals this angle implies that these 4 points lie on a circle. And if you draw a circle around them, indeed they do lie on a circle. Very cool. And now we can use the cyclic quadrilateral to chase around more angles. In fact, what you can do is you can show that this angle is equal to this angle because they're both opposite the arc QC on the triangle. But then you get that this angle, CDB, is actually equal to this angle using the large circle to chase it, right? Um, Using the large circle to chase it, you get that these angles are equal. So you have this red angle up top, or sorry, this red angle here. Using the small circle, you can see that's equal to this red angle at the bottom. Then using the large circle, you get that it's actually also equal to the red angle right at the top. And once you have these two angles, CAB and CPQ, once you get their equal, then you get that these two golden lines here are parallel by equal, corresponding angles or whatever. Great. So another example of a cyclic quadrilateral that was hidden that you had defined that you can then use to get more information, right? In our case, the red equal angles, which we wouldn't have had without finding the cyclic quadrilateral. Cool. Okay, let's go into some hard problems now. I don't know. Are these really harder? I don't know. Okay, so for this problem, just a warning again. Hope you remember the alternate segment theorem. Yeah, that's gonna be useful here. And also hope you remember how similar triangles work. We're gonna need some similar triangles. Either that or PowerPoint. If you guys know PowerPoint, if you don't, that's fine. We can just use similar triangles. Right? Okay. I shall quickly. Just someone wanted the IMO reports. Hey, that's fine. Oh, that's right. Okay, so we have a point. Okay, so we have this. Oh, and also, of course, the equal-tangent property is going to be useful here, right? Because we literally have a circle, which has a point that has two tangents being drawn to the circle from it. So basically, this is like what the question means, right? It's we have a circle here. Holy crap. We have a circle, and we have a point O, that's just any point, touching the circle at points A and B. And we're gonna draw another line here, parallel to OB, passing through A. So it looks like this. We copy it over, parallel, and it's going to intersect the circle again at some point C. Right. And finally, we're going to well, not finally, but we're going to draw this line with the segment OC, which is going to meet the circle at not D, but weirdly enough E. Sure, interesting naming. And finally, we want to show that AE bisects OB. So we want to show that OD equals OB. And where these two segments here are parallel. Well, I can't really say that as well, but maybe I'll double check it. Okay. Um, what to do? I think the first thing to do when you get a bunch of random conditions like this is to just chase around angles, right? It's just to see, what angles. Sorry. Okay. Do you want to? Okay. I'll quickly draw up the. Do you mean the alternate segment theorem? Oh, wait, do you even need the alternate segment theorem? I might have lied. Oh, well, I mean, I didn't really lie, but okay, you either need the alternate segment theorem or you need to know PowerPoint. Um. Okay. Okay. Wait. I think I'll just wait. This over that equals. Oh, never mind. Okay, you definitely need it. Yeah, sorry. Yeah, I almost forgot how to solve it, but yeah. Okay. I'll just quickly draw it up on the side again. Right here. Maybe I should have it on a different whatever, who cares. I'll just try to be quick with it. This angle equals this angle. Yeah, that's what the theorem is. Two green angles are equal. Um, when you have that this is when you have that this is a tangent, you have that these angles are equal. And you have you know equally on the opposite side you have the same thing, right? But okay, that's what theorem is. And okay, there's another question: is A able to exist inside the circle? No, it's not because you can't. Yeah, like if I have O inside the circle, I can't draw tangents from O to the circle anymore, right? Like I can only draw tangents from O to the circle if O lies outside the circle. Okay, so we have some tangents. So let's try using the alternate segment theorem, right? Um, so first we will consider uh, this angle here, this green one, and what is this angle equal to? If if you look real hard at what we have over here, and maybe think about it a bit. Again, remember this angle, which saddles, which is like kind of like adjacent to the segment GJ, is equal to the angle that is opposite the segment GJ, right? So if we go back to our diagram here, we have this angle which is adjacent to the segment EA. It's like like pressed up against the segment EA. Is going to be equal to the angle that is opposite EA. So this angle, ECA. Cool. Um, so we have these two angles are equal. But also notice that we have parallel lines, right? So we can further chase this to get even more equal angles and say that by like alternate angles being equal on a you know like across two parallel lines, which is like the common the quote unquote like Z shape, right? We get that this angle is equal to this angle as well, right? COD. So we have all three of these green angles are in fact equal. Um, and that's interesting now because if you look at this triangle ODA, um, okay, well, okay, if you look at the triangle ODA, um, actually, Hmm. Let's try using the alternate segment theorem on on the other tangent as well now, right? Actually, do you guys want to? I feel like there's too much teaching, but I might introduce a new theorem. Should I? Uh, I think I'll just I'll just full exposure, right? Okay, I'll just I'll introduce something else, right? Okay, sorry, but should I? But, I don't know actually. I feel like I don't want to be like cramming too much into this one lesson. Mm, that's okay. Okay, I won't. But if anyone wants to do any further reading or further learning once these lessons have stopped, the handout that I've linked to this lesson is just like a 250 page whatever textbook called A Beautiful Journey Through Olympian Geometry. It's available for download for free on the internet, so it's not pirated or anything. And it's a very nice book. I actually used it myself when I was starting out. I think it's got like problems with very nicely explained solutions, and it's got more practice problems at the end if you want to try them out. Um, yeah. So if you want to learn more, you can go read that, right? For now, I'll just solve this with similar triangles. Okay, let's connect up these segments so that we can use the alternate segment theorem on point B here. Because note that like to use the alternate segment theorem, you kind of need like a triangle first, right? Without this triangle IJG, you don't really have anything to use the alternate segment theorem on. So we're going to create this triangle here by introducing these new segments EB and BA. And what we're going to do is we're going to find that these angles, so we have DBE is, well, again, it's, pressed up against the segment EB, right? That's kind of the way I think about it. It's pressed up against the segment EB. Therefore, it's going to be equal to the angle opposite EB, which is BAE here. So we have the green angles equal and the red angles equal. Okay, cool. And point C is kind of almost irrelevant now, right? I don't really care about it. So I'm just gonna hide point C now. Okay, okay. Okay, let's focus on the important stuff. We have these green equal angles and we have these red equal angles, and we want to show that the in fact, even the circle is kind of unimportant now. We've kind of extracted all the information that we actually need from this problem. We have that these green angles are equal, these red angles are equal, and we want to show that angle or that point D splits the segment OB in half. So what we're going to do is we're going to actually use similar triangles. So whenever you have well, notice that well, when you have angles that are equal in this configuration, you're always going to have similar triangles. And the reason is if you look at triangles OED and triangles like OAD, right? So these two triangles, which are kind of like inside each other, you see that they share this common green equal angle, right? But they also share this common like large angle here, which I'll mark, maybe I'll mark in a different color, like orange or something. We see that both OED, so a triangle OED has a green angle and an orange angle, right? But triangle OAD also has a green angle and an orange angle. And when two triangles have two angles that are equal, the third one must also be equal from the sum being 180 degrees. Therefore, the triangles have all three equal angles, so they are similar. So actually, we have that angle OED here is similar to angle OAD. God. Wait, let me see if I can pull up like a whiteboard or something. Or like if I can just use a pen. Okay, that's good, I think. Um, so if you like kind of like unravel like this, right? O, so that should be a D. O, D, and E. O, D, E. Looks like that. Um, and in A, so this is the green angle, right? Green. And this is the orange angle. It's oriented like this, right? But if I um but if I look at this triangle O ADO, I still have green here and I still have orange here, right? Excuse my handwriting. Um ADO. Okay, obviously not the scale, right? The bottom triangle here should be much larger, but I'm just here to show that they're kind of the same the same like shape, right? They're similar. It should be a D. Okay. So what does that actually tell us? Remember that whenever we have similar triangles, we can interpret it as a ratio condition. And that's kind of good, right? We kind of want to interpret it as a ratio condition because, well, we're dealing with lengths here, right? We're trying to show that OD equals, dB. So if we can um if we can interpret something as a ratio, then that's good, right? Let's try to figure out what lengths are equal to what other length or whatever, right? So okay, the key length we're dealing with here is OD, right? That's the one we're interested in. So let's try to do some ratio using OD, right? Okay. Um, in fact, it's nice because OD is in both of the triangles. So OD here corresponds to the like middle length, but OD in the bottom one corresponds to the shortest length. So okay, why don't we do something like in the top triangle, let's calculate the ratio of the middle length to the shortest length, right? In the top triangle, that looks like OD over DE, right? That's middle divided by shortest. And that ratio should remain the same in the bottom triangle because the triangles are similar, right? So in the bottom one, that is AD, right? That's the middle one, divided by OD. And if we multiply to get the ODs together, we see that OD squared equals AD times ED. So what we've shown is that this length squared equals AD, this one, times this one. Okay, that's cool. So what if we do the exact same analysis on the bottom of two pairs of triangles, right? This triangle and this triangle. I'll spare you guys the details just because it is literally the exact same thing, right? You can kind of see it just by how the problem is pretty symmetric, right? There's no reason why one side should be different from the other. The green side, if we do the same thing for the red side, we should get the same calculation. And in fact, what ends up happening is you get that BD squared equals AD times ED as well. Um, so you have that this thing squared equals this times this, but this times this equals this thing squared. Therefore, OD squared equals BD squared. And if this was algebra, you would need to say that OD is plus or minus BD. But we know that the lengths are positive, therefore you can just square root both sides and just say that OD must be the same as the same length as BD, right? The sizes are the same. So yeah, cool. Well, we should know, yeah, then that's what I want to show, right? Great. Um, cool. What's the next? Okay, well, let me just clear everything here. Next problem. Problem 5. Let P be a point inside circle gamma. Omega, sorry, my bad. Oh, this is a pretty short problem statement, actually. I'll just quickly delete everything again. Wait a minute. Yeah, I'll leave the alternate segment theorem like thing up just because I think that might come in handy for the next problem. Cool. So let's start with our circle here. Um, God, what's going on? What? No, crap. And okay, well, this is, I mean, it's meant to be called circle omega. Let's see if I can copy this and rename it. Great. And we're gonna have a point P, which is just any random given point, arbitrary point, which is inside the circle. And what we're gonna do is we're gonna like consecutively, well, like just take a bunch of chords through P. So an example of a chord through P is something like this, chord CD here, right? Um, and we're gonna take the midpoint of this, and we're gonna mark it. Okay, well that's kind of, yeah. So something like this, right? And we're gonna mark that as point E. Well, really, what's the thing is that as we like move this, as we take like as we keep taking more and more like chords and computing, finding their midpoints, all of those midpoints, so all these different E's should always lie on a circle. And you can, see that graphically if I, have a trace on here and see that, it has it leaves a nice circle. So, okay, I guess I'll maybe go over how you might, um, like try to do this problem, right? So, like the way, oh, okay, by Ewan, Ewan, Ewan. Okay, I'm not sure if he already left, but I think he already left. Um, okay, so the way you do this is what you want to do when you have something that says for every blah blah blah, we have blah blah blah, right? Is let's take specific chords that go through P to get information. So what are some like nice chords that we can take that go through P to that gives us like information, right? Like what are some special chords that we know in a circle? Okay. Well, one special chord I can think of is the diameter, right? What if we take CD to be the diameter, which would to be the diameter which passes through P? Okay, well the midpoint of the diameter is always the center of the circle, right? That's like a pretty basic fact. So we've shown that the center of the circle, O, must lie on the circle. Cool. Um, we've shown that at this point, O lies on the circle. What is another point that might be another chord that might be useful? Well, if you look here, if we choose the chord such that P is the midpoint of the chord, then we've shown that P itself must lie on a circle. So we've shown now by taking special chords that pass through P, right? First the diameter, then the chord that has P as its midpoint. We've shown that both O and the center and P, the point, arbitrary point, they must lie on this special circle that we, supposedly have, right? But something else that we can notice is that because the circle is kind of defined symmetrically, right? Um, there's no reason why like O and P shouldn't be symmetric about the circle, right? Like, there's no reason why O and P should be like near the quote unquote like top of the circle or the bottom or like next to each other. It feels like O and P should be like evenly spread out about the circle because of kind of like the symmetric nature of the problem, right? I mean, you literally have a circle and a point, which is about like as like general as it gets, right? So, or as symmetric as it gets, right? And that along with maybe just taking a bunch of chords and just trying to see like where the midpoints lie up. You want to conjecture, right? You want to you want to guess, right? Hypothesize that maybe, just maybe, uh, the circle that we're interested in is the circle which is OP as its diameter. And if you see here, it's pretty clear that like it is, right? Like it's a circle which has the center O and at one end of its diameter and then P at the other. And once we've guessed that this is the correct circle, we need to prove it. And the way we can prove it is we can the way we prove this is we can just show that the point E, the midpoint here, must always lie on this circle. And what we're going to do again is we're going to use Thales' theorem again. Remember, the Thales theorem tells us that if you have, well, it tells us two things actually. It tells us that, well, it's an if and only if condition. So I earlier I stated that when you have a diameter of a circle, the angle subtend or the angle like that you get when you join up the ends of the diameter to a point in the circumference is 90 degrees, right? That was the configuration I showed. But the converse is also true. If I have a um if I have a point um such that when I connect up that point to the endpoints of a diameter and the angle is 9 degrees, then the point lies on the circumference of the circle. So to prove that E lies on the circle with OP as a diameter, all I need to do is I need to show that angle OEP is 90 degrees. If I can show that OEP is 90 degrees, right, then I'm finished by the converse of Thales theorem. Okay, so does anyone like have any ideas on how you could show that OE is perpendicular to CD? Okay, well, I'll just spoil it. It's kind of just well known. I mean, it's because E is the midpoint of the chord CD, and the perpendicular bisector of a chord always passes through the center. I mean, you can show this with you can show this with similar triangles, right? Or congruent triangles. If you connect up the radius, the two radii OC and the other radius OD, then what you can do is you can show, well, okay, well, I'm not gonna prove it here with all the like the proper like side angle side like congruency or whatever. But I guess you can almost argue by symmetry. Right? I mean, it's just kind of a well-known fact that you should know, or and you should remember at least, that whenever you have a chord and you take its midpoint, then like the perpendicular from the midpoint pass through the center O, right? Um, or in other words, when you drop a perpendicular from the center to a chord, it will pass through the midpoint. And since E is the midpoint, we know that OE is perpendicular to CD. So we've shown that OE P is 90 degrees here, which shows that the point E lies on the circle with diameter OP. And this argument holds no matter what chord CD we choose. Therefore, the midpoint of this arbitrary chord CD will always lie on this fixed circle. So yeah, problem done. Okay, let's move on to I'll go through one more problem. I think we have time for problem 6. And these hardest problems are quite hard. Actually, I quite like this problem 8. Maybe give it a try if you want. I remember this question stumped me for a long time back when I was starting. And when I found the solution, I thought it was very, very nice. Or when I read the solution, at least I didn't find the solution because I wasn't good enough. But I really like this problem. Question 7 is what is question 7? Question 7 is okay, and question 9 is I just put in here the problem. But I would really recommend trying question 8. Actually, I don't know, it's quite hard. Maybe just work through the textbook I sent. It starts off pretty easy, so I think you guys should all be able to get through it relatively okay. Okay. Anyway, our final question today. Let's do it. Okay. Mm. Okay, I think this problem's got quite a lot of solutions, right? Quite a lot of different ways of doing it. If I remember correctly, on the solution packet for it, this is the Australian Maths Olympiad. I think there were 10 different solutions, but some of those solutions, I mean, they were using really advanced like projective stuff, right? So, I mean, there's only like there aren't that many like easy solutions, yeah. So the basic premise is that we have here we have a a triangle ABC where angle ACB is in 90 degrees. So we have a right triangle that we start with. And we're gonna take this oh sorry, I should probably include the circle back in, shouldn't I? Oops. Okay, we're gonna have this circle of the circle of ACB. Sorry. And we have the tangent at C to the circle and intersects point A, B at D. Then we take the point E, which is the midpoint of segment CD. That's E. We connect EB up until well we connect E. Okay, point K here is defined as, sorry, I'll change it because it should be point F really. I'm not sure where point F is, so huh. I'm not sure. Yeah, I'm not sure why it's point K, not point F. Um, okay. Yeah. So point F is here such that AF is parallel um CD, right? Okay, I don't have much decoration with this, so I'll just I'll just color the parallel lines orange like I've been doing before. So these orange lines are parallel, and we want to show that CF is perpendicular to AD. So we want to show that this angle here is a 90-degree angle. Okay, I'll quickly just go over the solution just because class should be ending soon. But the key idea used throughout most of the solutions, right, is you have to introduce a new point, as you often do with tricky geometry problems, right? You and the motivation, right? The reason why you might introduce this point is because it gives you like nice like angle chasing things, right? Because okay, before we introduce this point, right? Before we introduce this point, let's chase around some angles. What we might notice is that by the alternate secant theorem, we have that this angle, if you look, right, oh sorry, wait, where was the diagram I had? Okay, go. Where the hell did everything go? Hold on. I'm finally. What? Wait a minute. How did I just lose everything? Okay, let me just like. Oh, great! I found my stuff. Whoops. Okay, sorry. Hey, if we look at this thing, right? Again, we remember that the angle which is pressed up against the segment is equal to the angle that's opposite the segment. Oh, great. So if we have this red angle which is pressed up against this segment CB, it must also be equal to these two angles which are opposite the angle CB, right? Color that red. Color. So these red angles are all equal. Cool. But we need something a bit more, right? Oh wait, sorry, wait. This angle is this red angle is not equal to the other two because it's not in the circle, right? Um, okay, so we have that these two red angles equal, but we need more, and that kind of motivates us to maybe connect these um these lines up, right? Because when we connect when we connect at the so when we connect these lines up, what we end up getting is we end up getting because remember that these orange lines here are parallel by alternate like angles on parallel lines, we get that this angle CKA must also be equal to the red angle. Okay, cool. So how do we finish it from here? Well, like the final thing to notice here, well, not maybe not the final thing to notice, but one important thing to notice here is that if you look at if you look at um the triangle ACK now, right? It's got right angle. It's got right angle angle ACK, right? Um, and maybe ah, actually it's a bit hard, but what you have to notice is that you have to notice that so E is the midpoint here, right? E is the midpoint of this triangle. Um, and you notice that triangle CBD is like similar to triangle KBA, right? Because we also have these pairs of equal angles, right? You have that CBD here is equal to angle FAB by again alternate angles across parallel lines. And you have that these red angles are equal, these green angles are equal. So you have that you get a pair of two similar triangles. Um, in fact, it's kind of like a mapping. Like you can kind of imagine like inverting this triangle DBC, right? I'll just use my thing, right? You can kind of think of like a scaling factor through B, which maps C to K, which maps D to A over here, and it maps E to F because they're all similar triangles, right? Like it kind of inverts, it twists the triangle and inverts it across B while keeping the proportions of the triangle like very similar. You can prove this more rigorously with like just with like ratio properties from similar triangles, right? You can go look on the AMT Australian Mass Trust website for the official solutions if you want to see the more like complete solution. But the general gist of the solution, right, is that because you have these two like because you have the midpoint E mapped through B goes to the point F here of the triangle, you actually get that these two uh these two lengths, F is also a midpoint of AK because E is the midpoint of CD, and you're like kind of mapping E through B to F. So now that we have a midpoint and a right angle, remember from before that we get three three like a triple of equal segments, right? Equal length segments. Um, so and I guess one way you can quickly think of seeing this is that um, if you look at a circle containing these 3 points, by the converse of Staley's theorem, because we have a right angle here, we must have that AK is the diameter. Therefore, F is the center of the circle. Therefore, FA, FK, and FC are all radii of the circle. So they're all equal length. And we're like almost done here now. Right? Notice we have. Well, let's keep chasing more angles. I mean, that's a great thing to do whenever you're trying to make progress, right? If you can chase around angles, just do it, right? If we look at the isosceles triangle FKC here, we get that angle FCK equals angle C or FKC, right? They're both like angles next to the legs of the isosceles triangle, therefore they're equal. So they're both the red color as well. Right. So we have these two angles being equal, FCK and well FCB and BC. Well, okay, the important pair of red triangles, right? Like I can like get rid of all this crap now, right? The Like this, not important, not important, not important, not important, not important, not important. Honestly, wait, you're not important. Sorry, but you're not important. Sorry, but you're not important. Yeah. Oh, I got rid of the. Yeah. If we just look at this, this shallower diagram that we have left here, right? Once I've kind of cleared off everything. Remember from before, when we have something like this, right, where we have two equal angles and they're kind of sharing this common angle here, right? If you look at this angle um here, this black angle here, triangles CLB have a red angle and a black angle, but triangle BAC also has a red angle and a black angle, right? So if I look at triangle ACB, I have red um and I have black here, right? But then if I look at triangle CLB, I also have red here and I have black here, right? CBL here is black. So what that means is that the third triangle, right, the last angle, sorry, must be equal. And the top triangle is a 9-degree angle defined by the problem in the first statement. Therefore, in the bottom, it must also be a right angle. And that corresponds to this angle right here. It's a right angle, which is what the problem asks us to prove, right? Show that, it's a right angle. So you're done by similar triangles. So that's very cool. So you had to chase around angles and use that as maybe motivation to, connect up two lines to introduce a new point to then get a right triangle, which gives you some equal lengths, which gives you more angles, which gives you, okay, yeah. It's a bit of a complicated problem, but that's kind of how it is, right? It's like one step at a time, right? Chase angles, then find properties, then like chase more angles, and you take it one step at a time, finding more and more information, and until eventually, you have enough information to complete the problem. Yeah, cool. So that's all for today. Um, yeah, just 2 students left. Went a bit over time, but yeah, I guess that's my fault for starting, but late anyway.